Test, test.
Hey guys, what's going on today? How you doing? Welcome back to USW. I'm not but I'm here to talk to you guys about the Maker Games. Does anyone know what Maker Games are? Is anyone registered in it right now? A couple up here. Anyone else? Okay, cool, awesome. The Maker Games, guys, are a rapid prototyping competition and course. It's run by the faculty in engineering, and you're going to submit a proposal to solve an industry-specific challenge. So we have 15 industry partners, ranging from Accenture, the Australian government, defense innovations, BAE systems, you name it, you cross the board, construction, defense, foreign affairs, and just some really cool stuff as well. Give you just a quick, brief overview of what the Maker Games are. It's an award-winning competition, of course, as well. Last year, we won an AFR Higher Education Award for Industry Innovation. So you guys are going to get to work with academic mentors, industry mentors. It's about a 1-to-1 ratio if you get into stage 2, which is term 2, and 360 is your course. So really, really amazing opportunity, guys. Who needs industrial training hours still? Pretty much everyone. You don't even need to raise your hand. It's a requirement for engineering. You have the opportunity to win industrial training hours, an internship, a job if you don't have one. Because if you're going to be working with your industry partner for a term, every week, every 2 weeks, you're going to develop a really, really good relationship. Our top 2 teams from 5B and D systems last year have been approached by 5B lawyers. They've won jobs and internships, won awards, and they've also won an international trip. Little wire on the bottom. So just on the bottom point there, guys, last 2 years we've gone to California. First year was Silicon Valley. Last year we did Silicon Beach outside of LA, where I took the winning team. This year it's going to be to Asia, to one of our partner universities. We also went to Netflix. That's with Ben Buchanan. He was, I believe, an electrical alumnus from 2006. If you watch Netflix and you watch a Disney movie or you watch a Warner Brothers film, Ben negotiated $2 million deals for the studios, at the Netflix studios. So that was pretty cool. That's the winning team from BE Systems. We got a few videos online. If you head to the Maker Games website as well, here's how to register, and you can get in contact. That link is actually wrong. We've updated our server, so it's a new link. But you can go to, like I said, makergames.com, event road as well, and or you can just contact me at the Maker Games. My name is Ben. And we have our industry night on March 15th, so in 2 weeks, 2 Fridays from now, you'll be able to meet all of our industry partners who are going to be coming on campus to be at the World's End Makerspace. They're going to do a 2 to 3 minute pitch to tell you about the challenge, their company, and what they're going to bring to you to help you guys out and have a user experience. So you get to meet them after, expand your network, and then you can create a proposal with your small team, and then try to win and get into this competition course in turn 2. It's a pretty amazing experience, guys. Is anyone interested by chance? Matt, does that sound pretty cool? Yeah, you, Matt? Sounds good. Spring training for baseball season. Oh, I would shout that. Who else is interested? Yeah, you, Ben, too. Yeah, you as well. Oh, that's perfect right there. Anyone else? Oh, yeah. Oh, well, at the back. Oh, no. Anyone else? Let's go this side over here. Who wants one? Sorry, guys. If you come to all this stuff, guys, we got lots of swag, lots of merch. Who likes wearing funky socks as well? I don't have them here, but come around next time. So, thanks a lot, Alan. Appreciate that.
No problem.
I don't know if it's going to log me off, but that's fine. Let's switch ahead. Cheers. Thanks a lot. Cheers, guys. Have a good one. Have a good weekend.
Good. So today we're going to talk about how to classify different types of tasks and different types of agents. And then we'll talk a little bit more about Prolog. And if we have time, we'll just start to talk about path search. Okay, so as I was saying at the end of last week, there's a lot of different types of AI tasks we're going to discuss in this course. So we'll talk a bit about One+ World last week, and we're going to look at RoboCup Soccer. Then next week we'll be looking at path planning, so sort of mazes and graphs and robots. And then after that we'll look at path search puzzles, so how to solve Rubik's Cube or the 8 puzzle or the 15 puzzle. Then we'll look at games, adversarial games, so board games, dice games and card games. Constraint satisfaction problems like Sudoku. And this is just in the first 6 weeks of the course. And so we're looking for a unified framework, and we have this kind of model of an agent acting in an environment. So the agent has sensors and it has actuators, and so it perceives things from the environment and acts on the environment. I used to use a slide for this that was supplied from the textbook, but we kind of made up our own one. The thing that was missing in the textbook slide was this arrow here. So the environment often has its own internal dynamics. It may continue to change even when the agent isn't acting. So the acronym that's used in this textbook is PEAS, Performance Measure, Environment, Actuators and Sensors. I think they just kind of juggled this around so that it could be pronounced. Really, logically, when we think about a task, we usually think about the environment first, and then the actuators, and then the sensors, and then the performance measures. So a more logical order would be EASP, but it's hard to say EASP. So they put P at the beginning and made it PEAS. So we looked at these examples. So in chess, the performance measure is you get 1 point if you win and 0 for a loss and half if you draw. And then we looked at this example of the automated taxi. So in the tutorials or the online activities and the tutorials, just have a look at a couple of examples of how to go through this. Okay. Now, I mentioned, so we mentioned about the automated taxi. Now, in terms of, performance measure, safety is very important. As you probably heard about that terrible incident where a self-driving car killed a woman with a bicycle. That should be paramount, but then these other goals are to reach the destination, maximize profits, and so on. This is the environment that you have to deal with. The actuators are what you yourself normally would use when you drive a car. So you've got the steering wheel, you've got the accelerator, the brake, the horn, and then you may have a speaker and a display to interact with the human passengers. Now, in terms of sensors, this is one of the entries from the DARPA Grand Challenge a few years ago, and we can have a look at it's interesting to have a look at what kind of sensors were on this vehicle, because it's similar to what's on the self-driving cars of today. So you've got a GPS. Well, this has 2 GPSs, primary and secondary. It's got a camera, it's got a few different cameras. So it's got one camera mounted on the top here. It's got another camera mounted here behind the windscreen. Sometimes they'd have a camera mounted at the front of the vehicle, but more likely you have other types of sensors such as either sonar or radar. And this thing here is a laser rangefinder. And now some of these things, and then you've got other kinds of radar and rangefinders. Some of these things have been superseded since. So these, if you look here, there's actually a series of laser rangefinders on the top. So these sensors, lasers kind of scan across, they sweep across, and if there's an obstacle, it tries to detect the distance to that obstacle. Now, there's always noise in these sensors, so you have to have algorithms which filter out the noise and so on. I'm not sure. So they had these 5 at the top, and then a later model just had 1 at the front. Sometimes there may be technology that's superseded this. It may be you could replace this with a Swiss Ranger or something, but you need some kind of sensor that detects objects and how far away they are. Okay, we had a look at the Wumpus world, how to describe the environment and the performance measure and the actuators and the sensors. This, let's just quickly, we looked at some examples last week, but we'll just quickly remind ourselves of this Wumpus world. So, let's say you start here and you don't detect anything, and then you come up here and you detect a breeze. So the breeze tells you that there's a pit in one of the squares next to this, but you know it's not that one because that's where you came from. So the pit could be there or there. So then we go back, and when we come over here, we detect a stench, but no breeze. So because we detect a stench, well, what can you deduce from this? Where's the Wumpus and where's the pit? And why? So here we detected a breeze but no stench, and here we detected a stench but no breeze. Who can tell me where the Wumpus is? 3, 1, yes, that's right. It's in square 3, 1. The Wumpus has to be here because if the stench here tells me that the Wumpus is here, here, or here, but if the Wumpus was here, we would have detected a stench when we were here, right? So this shows you that you sometimes have to, in order to make these draw these conclusions, you sometimes have to remember what you saw before, and you sometimes have to do some logical reasoning to figure out things about the environment. Right? The Wumpus is here and the pit is there. And we can keep going. All right, so we want, we're looking at this great variety of different AI tasks. What we want is a kind of unified framework that we can use to classify different kinds of tasks or understand what makes one task harder than another task, or what are the particular challenges of a task. Now, so these are taken from the textbook. Again, there's 8 different attributes. Some of them are like binary, so with the opposites. So they can. Well, I'll come back to the top one, but okay. Sorry, let me look. I think I'll get the definitions here. Simulated, static, discrete, fully observable, deterministic, episodic, known, and single agent. And then on the right-hand side is the opposite of each of those. So if it's not discrete, it's continuous. If it's not static, it's dynamic. This is a one-sentence description of each of these. Again, mainly taken from the textbook with slight edits. But it's... And you're expected to know this, but it's the best way to understand this is to look at a particular example, and in this case the example is chess versus RoboCup. Okay, so chess, I'm sure you're all familiar with chess or similar board games. Chess was, for a long time, chess was a kind of driver of technology in computers and artificial intelligence. So a lot of algorithms, a lot of work went into faster hardware and better algorithms to kind of play chess better. And then, of course, in 1996, Deep Blue beat Kasparov. And people were sort of looking around for maybe another kind of grand challenge that could drive further research, but with different attributes to chess, and a consortium led by Hiroaki Kitano at Sony in Japan and others eventually came up with this kind of RoboCup soccer as a new kind of challenge. So let's try to understand what's the difference between chess and RoboCup. So first, I'm sure some of you may have seen videos of RoboCup before, but it's always helpful to have a look at some of them again with keeping these ideas in mind. So let's see. These are some of the older robots. This is the old days when we had four-legged robots. We use two-legged robots now. I think there's a couple of, if you look on the OpenAI side, there's links to a couple of more different videos. Yeah, I like this. You see that guy was, this is part of the, well, I mean, we could talk more about this later. Maybe it's worth talking a little bit about how this programming is done. So you need a mix of low-level and high-level coding. So you need low-level coding for the vision and the localization. So the robot has a camera. Sorry, where was it? Sorry, let me just back up for a second. It might be instructive, first of all, just talk about what kind of sensors the robot has. So this is one of the older dogs. So what sensors does this, if we were going to come up with a P's description of the RoboCup domain, well, the okay, so the sensors, it's got, well, let's first of all talk about the actuators. What actuators does this robot have? Sorry? What can it do? Motors, right. So it's got motors in each leg. It's got a motor at the elbow and at the shoulder. It can move its head up and down and twist it around. It can wag its tail, which is useless but cute. It can also make noises, so it's got a speaker, and it can open it and close its mouth. Right? Now, what about sensors? What kind of sensors does this robot have? Sorry? Camera, yes. Where is the camera? The camera is actually in the nose. That's the camera there. It's also got it's got a Wi-Fi. It can communicate by Wi-Fi to a to other robots. It has got a microphone, but we did some experience with a microphone. the signal from the microphone was very noisy because there was a lot of noise because of the motors and so on. It actually wasn't that easy to. We experimented with having one robot say something and another robot understand it, but it wasn't that easy because of the quality of the signal. And another thing, it's actually got it's got touch sensors in its feet. If there's these little things that when it puts its foot down, it's little pad that sort of clicks up so it can tell when its feet are on the ground. It's got encoders which tell it the position of its various motors, and it's also got a little sensor that tells whether the mouth is open or not. Now that may seem useless, but in fact our team managed to make some good use of this, because if the robot, let me just go back to the video here. I wonder if we can see the robot shooting. Just have a look at when the robot shoots. You see how it kind of bends down and lifts up its legs and then shoots the ball like this. Now, it turns out because the camera is in the nose, once it gets into that position, the ball is under the chin, and so it can't actually see the ball. So sometimes it would happen that it lines up to shoot, but then another robot manages to knock the ball away, or the ball just bounces away, so the ball's actually not there anymore, but the robot still tries to shoot. So in order to avoid that, someone came up with this idea, well, the robot it opens its mouth, and then it lowers its head, and if the ball is there, the mouth will close. If the ball isn't there, the mouth won't close. So if the mouth closes, then it knows the ball is there, and then it'll shoot. If the mouth doesn't close, it knows the ball is gone, so it will go and do something else. So sometimes you can come up with quite clever ways to use these different sensors. Okay, so you've got a mix of vision. So someone, I think, will have a dedicated lecture later in the course specifically about machine vision, but you have to process the feed from the camera to try to figure out where the ball is, where the goals are. In the early days, we had these beacons around the edge of the field with special colors that would help you localize, and the ball was a special color. It's all different now. They don't have these beacons, and this looks more like a black and white soccer ball, not an orange one. So there's vision, and then there's localization. So how do you kind of figure out where you are on the field? So there's those sort of things, and then you get this kind of high-level behavior. So this is a good example of a high-level behavior that robots might take on the role of a shooter or a defender, and then I think it often happens that several robots crowd around the ball, and sometimes in the confusion the ball sort of pops out. So this guy here is actually exploiting that. He's standing there waiting in case the ball comes out. Then he'll be able to exploit that opportunity and shoot for the open goal. Very good. Yeah. Oh, I wonder if we can get the sound. I don't know if I can get the sound here or not. I'll try to get the sound. Okay, so the first point of difference between chess and RoboCup is simulated versus situated or embodied. So simulated means that a separate program is used to simulate an environment, feed percepts to agents, evaluate performance, etc. Whereas situated means the agent acts directly on the actual environment. Embodied, the agent has a physical body in the world. So normally we think of chess as simulated and RoboCup as both situated and embodied. Now, you can always raise kind of philosophical objections to these things. So someone might say, well, what happens if chess is played on a physical board with actual pieces? Wouldn't it then become embodied? And this actually, I mean, I remember the very early chess machines in like 1981, they had a robot arm that they were very, the board would be here and there'd be this arm that was connected to the edge and you would make your move. I think you had to press, when you moved a piece, you had to press the square that you were moving from and the square you were moving to so that it would know what move you made. And then it would sit there and think for 3 minutes, and then this arm would come over and move a piece. But really, I mean, all of this was just kind of fancy stuff to try to distract from the fact that actually it played a very poor game of chess. So I think the answer to this we would normally think is that it sort of splits into two independent tasks. If you wanted to build a robot to play chess, you could assign one team of programmers to the task of deciding what move to make and another team to the task of having the robot physically pick the piece up and move it. And these two teams really wouldn't have to talk to each other at all. The two tasks are completely independent. So that's why we tend to think of this as simulated. And in fact, I think there's a video from about 5 or 6 years ago. Rodney Brooks, a famous roboticist, tried to take on the task of moving stones on a Go board. Not which move to make, but just a robot that would pick up a little stone and move it, pick up a stone from the bowl and put it on the board. And that's actually quite difficult. He allocated 2 months to try to work on this and actually was unsuccessful. The robot kept fumbling the stones and dropping them and stuff. Okay, then we move on to static versus dynamic. So this is the definition of static. The environment does not change while the agent is thinking. Whereas dynamic, the environment may change while the agent is thinking. So you can see this with RoboCup. If the ball's in front of the robot, in chess, you can take as long as you want within the time constraints to think about your move. The board is not going to change while you're thinking about your move. Obviously, after you make your move, some people get confused about this. Because the opponent, obviously after you make your move, then the opponent will make their move. So it's not that the board never changes, but it only changes when it's the turn of the other person to move. The board doesn't change while you're thinking about your move, whereas in RoboCup, you may have the ball in front of you, but if you take too long to think about what you're going to do with it, someone may knock it away from you. And all other things are happening around you as well. While you're sitting there, all the other robots are moving and so on. So this is static versus dynamic. Now again, you can make raise philosophical questions about this. In chess, you couldn't literally sit there for a year. Something would happen, so that the chess clock is ticking down while you're deliberating. And if you run out of time, then you're going to lose. So that's a very slight dynamics, but we normally tend to ignore something as simple as that. Then we have discrete versus continuous. So with chess, you're either on this square or you're on that. So the same with Wumpus World. You're either on this square or that square. You're not allowed to put a piece halfway between two squares. But in RoboCup, there isn't that discretization. both the robots and the ball move continuously throughout the space. So it's continuous in two senses. It's continuous in space, and it's also continuous in time. And finally, we get the question of fully versus partially observable. So chess is called fully observable. That means that the agent percept contains all relevant information about the world, whereas partially observable, some relevant information is hidden from the agent. So relevant information, right? So if you're playing chess, you can see where all the pieces are on the board, which is the information you need to play the game. Of course, there are things going on in the world that you can't see. You can't see the little girl playing in her backyard across the street, but that's not relevant to the task. Right? Okay, now this to see why RoboCup. So if it's not fully observable, we call it partially observable. That means you can see some things, but not others. Let me see if this will play. So in order to understand why RoboCup is not fully observable, it's helpful to look at what the dog actually sees. Now again, this is old video using the old model dogs, but this I find very instructive. This is what the dog actually sees while it's playing a game. So it's definitely not fully observable, right? This is a very rare frame, because in this frame you can actually see the ball and a beacon simultaneously. That's the ball and that's the beacon, but most of the time you can't see either of those things. There you get a slight. I mean, this really puts you into the mind of the agent and understands what when we look from the side and the agent or the robot fumbles the ball or can't see the ball, we think, oh, what a stupid robot. But then when you actually see what the robot is seeing, like in the days when we had the beacons, you would have to make use of this. From this image, you have to detect that there's something here, some blue and some pink. The blue is above the pink, and make use of that information. And in the meantime, you have to try to remember where you were on the field, the last place you remember yourself being on the field. And sometimes you can't. You almost never see two beacons at once. You see one beacon, and then a little bit later you see another beacon, and you have to use certain Kalman filters and so on to try to estimate your position from there. Okay. Yes. Okay. So again, we can start to have a bit of discussion about this. So what I showed you is the kind of standard platform league or the legged league. There's another league of RoboCup where you have your own robots. It's kind of sorry, it's a shame we can't hear the video here, hear the audio here, but if you look on the Open Learning website, you can hear the audio. Now, again, things have changed. So in those days we had a very small field. We had ridges at the edge of the field, and sometimes if the ball got stuck, the magic stick of the referee would come out to get the ball unstuck just to keep the game moving. And but I guess the point I'm trying to make here is that for this league, one of the things for this league was you were allowed to have an overhead camera. So with the other league, you could only rely on the vision from the actual robots, and the robots could communicate with each other, but they were not allowed to communicate with an external computer. But in this league, you're allowed to have an external computer, and you were allowed to hang a camera over the field. And it turns out that if you, and you see we put distinctive markings also on the top of the robots. Oh, here we go. Oh. It's better with the sound, but anyway. Well, it turns out, I'll say a bit more when we get to A-star search. I'll say a bit more about how we did the trajectory planning. But it turns out if you hang the overhead camera, you can figure out the location of the robots pretty accurately to the point where it's actually close to being fully observable. So again, this particular league, you could almost, in fact, and we could actually switch, we could run our software and switch back and forth between the simulation and the reality, and the functionality was almost the same. So you could argue perhaps that this particular league of RoboCup is fully observable, but not the other one. Okay, deterministic versus stochastic. So deterministic means that the current state of the world uniquely determines the next state, whereas stochastic means that there's some random element. Now again, the philosophers could come in and argue about this, but well, if you look at RoboCup, you see the way the ball kind of bounces in funny ways off the robots and goes in unexpected angles and so on. Now, a philosopher might come and try to argue, well, if you knew the trajectory of the ball, then you probably should be able to predict it. I mean, there's two kind of arguments, two objections to that. So, all right, so the non-determinism, it partly arises because of the physics can only be modeled with limited precision, but it's just more convenient to think about this as being stochastic rather than thinking about it being partially observable. But secondly, even if you could model the physics perfectly, the quantum physicists tell us that there would still be randomness due to quantum effects. Okay, so these are the 5 attributes which distinguish between chess and RoboCup. Yeah, and it's worthwhile to just go back and sort of revise this because they're sort of all related, but each one is actually a bit sort of different, distinct. Now then there are some other attributes in which they're the same or which they share. So in the textbook they talk about episodic tasks versus sequential tasks. Now, both chess and RoboCup are regarded as sequential because you have to do a long series of actions before you get a performance measure. Now, an example of the kind of task that would be episodic is like medical diagnosis. Like you have a system that looks at a scan of a patient's liver and tells you whether they have some kind of disease of the liver. So because each patient is separate, you get the scan from one patient and you make a diagnosis, and then you get a scan from another patient, and you make a diagnosis, and each scan is completely independent of the others. That would be an episodic task, whereas a sequential task, you do a long sequence of actions, and then you either win the game or score a goal or whatever. So this is this distinction between sequential and episodic are known. So this is, again, you've got to be careful about this. So when we talk about known and unknown, we're talking about basically the rules of the game or the physics of the environment. So it's different from observable. So both of these are known because in chess you know the rules of the game, you know what's going to happen when you move a piece somewhere. In RoboCup, the same thing, you know what the rules of the game are. So there are some situations, people have done research where you try to play a game and you actually don't know the rules in advance, and then you have to kind of guess the rules as you go along from the rewards that you get. So that's obviously, or the sequence, you do something and you observe what happens, and then you try to guess what the rules of the game are. So that's obviously much harder. And this also illustrates, when we talk about classifying a task, it's the way information is presented to the agent is part of the task. So if an agent's playing a game but isn't told the rules of that game, it makes the task very different compared to if it was playing the same game but it was told the rules in advance. And so the task encompasses all of these things about how the agent interacts with the environment. And I think the last one here is multi-agent. So both chess and RoboCup are multi-agent because in chess, the opponent is also acting on the environment. In RoboCup, the other robots are acting on the environment. Now, if you want to ask what's a single agent task, well, the most obvious examples would be solving puzzles, like Sudoku or Rubik's Cube. There's only one agent that's doing things. Card games, solitaire card games, a single agent. And okay, so that's the whole list of the 8 attributes. So is there any questions about this? All right, so let's have a look at the Wumpus world and try to see how we would classify it according to these attributes. Well, in some ways, the Wumpus world is like chess. It's simulated, static, discrete, sequential, and known. Right, so let's think about this again. So the Wumpus world, obviously, it's simulated. There isn't a real Wumpus. It's static. The world doesn't change while you're thinking. It's discrete because the Wumpus has to be in one square. Everything has to be in one square or another, not halfway in between. And it's discrete time steps. It's sequential because you have to do a whole series of steps and get back with the gold. And it's known because you know the rules of the game. Okay, so it has those things in common with chess. Now, how is it different from chess? Well, chess is fully observable. The Wumpus world is only partially observable, right? Because you don't know, at the beginning of the game, you don't know where the Wumpus is. You don't know where the pits are. You don't know where the gold is. So there are things in the environment that you can't observe. We normally consider it to be deterministic. We normally consider it to be deterministic but partially observable. So normally the way the game is implemented, the location of the wumpus and the pits is chosen randomly at the beginning, and it's fixed, but you just don't know what it is, right? So when you're playing, you can't tell the difference. Maybe you don't, I mean, if the wumpus did move while you were playing, you wouldn't be able to tell that it had moved, right, if you haven't seen it yet. But normally it's decided in advance. So it's partially observable, but it's deterministic. And what about single or multi-agent? Well, normally we consider the wumpus world to be single agent. And the reason is because the wumpus, even though the wumpus is in some sense your enemy, we think about it as a natural feature because it doesn't move and it doesn't make any choices. The wumpus doesn't move, it just stays where it is. And if you go to the place where the wumpus is, it will eat you. It's a very simple creature. So that's the reason we think of it as a natural feature rather than as an adversary. Now, if you had a version of the game where the wumpus moves around, and especially if the wumpus had a way of moving around, not randomly, but in a clever way to try to catch you or trap you somewhere, then we would think about it as multi-agent, but not otherwise. Okay, any questions about this? Yes? The person making the decisions, right? If there's something that makes an automated set of movements, well, okay, let's think about this. Let's say you're playing chess against a computer program. Would you consider the computer program to be an agent? Yes. So you don't have to be human to be an agent. Right. So this is interesting because it kind of teases out our understanding of the word agent. I think if it followed very simple rules, well, okay, I hadn't thought about this before, but what you raise is an interesting point. Let's think about Pac-Man. Okay, so in Pac-Man, for a long time it was not known exactly the strategy that the ghosts were following, and someone managed to, because the only thing that was available was this machine code, the original source code was kind of lost or not available, but by analysing the machine code, someone eventually managed to figure out the strategy that the ghosts were using. So I guess this kind of gets at your point, if I understand rightly. Let's suppose you're playing Pac-Man and you know exactly the strategy that each ghost is using. Maybe you would then consider it to be a single agent task because you know what the ghosts are going to do. But if you didn't know what the ghosts were doing, maybe we would then consider it to be multi-agent. I don't know. So it's to do with this. It's partly to do with simplicity. If the wumpus is following a really simple rules, then we'd be reluctant to regard it as a separate agent. But if it's doing something very sophisticated, we probably would. And also whether we know what it's doing or not. Yeah, maybe those are the things that. That's right. Yeah, it's a very, very good point. Yeah. Okay, so let's have a look at a few other different kinds of games and tasks. So backgammon, I don't know how many of you are familiar with backgammon, but this is a kind of game where there's a class of games where you roll dice and you move pieces around the board. And so there are games like Ludo where you just roll the dice and you move the pieces and you don't have much control over what happens. But backgammon is a combination between the dice rolls and making intelligent choices. So you roll the dice and then you have several choices about which pieces you can move, and you need to use some intelligence to decide what move to make. So it's a combination between luck and skill. And most of you, I think, are probably, if you're not familiar with this particular game, you probably played games like that, right? So it involves dice rolls. Now again, this is very similar to chess in the sense that it's simulated, it's static, it's discrete, it's sequential, it's known, and it's multi-agent. Now, what about the other attributes? Well, this is again where we can get into a bit of a philosophical discussion, but normally we think of these games as being fully observable but stochastic. So we believe that we can see all the relevant information, but then when we roll the dice, randomness determines what the dice roll is going to be. So that's the most convenient way to think about this, that it's fully observable, there's no information that's hidden from us, but there are random elements in the game. Now, this may seem subtle, but I did some work on backgammon a long time ago, and in practice, when you implement this in a computer, you don't have physical dice, you use a pseudo-random number generator, and it has to be initialized with a certain seed, and once you choose the random seed, in some sense those dice rolls are going to be predetermined. The sequence of dice rolls is predetermined. So it is possible to think about this as being it's possible to think about this as being deterministic but partially observable. Because you could say, well, the dice rolls aren't really random. Because I've chosen the seed already, the dice rolls are predetermined. It's just that I don't know yet what they are, right? So when you reveal the next dice roll, you could think of it as something that had been decided before but is now being revealed. Right? So, and this sort of feeds into philosophical. So there's a philosophical movement called the Neo-Calvinists. They believe in predestination. They believe that God has decided in advance everything that's going to happen, and we're just kind of observing it. So this feeds into serious philosophical discussions, but for the most part, generally speaking, it's more convenient to think about it this way, that it's fully observable and stochastic, rather than deterministic and partially observable. And if you were, some modern computers have a little sort of quantum chip in there that will generate a genuinely random number using quantum mechanics. If you use that, then it wouldn't be deterministic. And then we get to card games. Now again, I'm sure all of you, whether it's Mahjong or Rummy or Bridge, all of you are familiar with these kind of games. You shuffle some cards and deal them out. And you can see what's in your hand, but you can't see what's in your opponent's hand. So how do we analyze these games? Well, again, simulated, static, discrete, sequential, known, and multi-agent. Now again, okay, what stochastic versus deterministic? Well, you can sort of split hairs about this too. If you shuffle the cards during the game, then it would be stochastic. But sometimes what happens is all the cards are shuffled beforehand and put in a pile, and then every time, during the game, sometimes you pull a card off the top of the pile. So you could consider that to be deterministic in the sense that the cards are just sitting there. I just don't know what the next card is yet, right? But, and this is an important point, these games are definitely partially observable. There's no question about that at all. It's partially observable, and the reason we have to regard it as partially observable is because there's things that I know that the opponent doesn't know, and vice versa. So the opponent knows what cards they have, but I don't know what cards they have. So you've got this kind of asymmetry that different players in the game have different information, and this is different from, so with this backgammon, when the dice are rolled, everyone can see at the same time, it's revealed to everyone at the same time what the dice roll is. But with these games, it's not. There's information is revealed to one player and not to another. So we have to regard this as partially observable, and this is actually what makes, in some sense, this is what makes these games like bridge quite hard, because you have to, from what you observe, you have to deduce what cards the opponent is likely to have, and then what move they would make based on that information. So some of the a lot of when people have tried to write computer programs for bridge, for example, one of the programs, Jib, that was strong for a long time, the way it worked was when it came time to move, it would try to generate, it would try to guess what cards the opponent has. You know, it would randomly, it would try to guess a set of cards that the opponent could have, which is consistent with what you've observed, and then it would say, well, what move would I make if they had those cards? And then it would do the same thing. It would generate a different set of cards that's also consistent, and then what move would I make? And it would do this like 100 times, and then out of those 100, whichever move was suggested most often is the one that I make. Right? So that's one possible approach to this, but it's difficult. Okay, now finally the issue of simulated, and after this we'll take a little break, simulated versus situated or embodied. So what's the opposite of simulated? Well, there was sort of a long discussion about this, and I think the consensus generally is that there are two different opposites of simulated. One is situated and one is embodied. And again, this Rodney Brooks that I mentioned was the one who has written most extensively about this. So this is from one of his essays from 1991. He says, the robots are situated in the world. They do not deal with abstract descriptions, but with the here and now of the environment, which directly influences the behavior of the system. Embodiment, the robots have bodies and experience the world directly. Their actions are part of the dynamics of the world, and actions have immediate feedback on the robot's own sensations. So if you think about an example of something that's one and not the other, So something that's situated but not embodied would be, for example, an airline booking system or a high-frequency stock trading system. So it doesn't normally have a physical body. It's all just sort of software running in the computer. But it interacts, but it's situated in the sense that it's trading with real money. It's when it makes a trade, and if it makes a profit or a loss, that's actually real money. It's not fake money. And the same thing if you go and book an airline on an airline booking system, you're really going to have to pay money for that ticket, and eventually you're really going to get on a real plane, right? So it's actually, it doesn't have a body, but it is having an impact on the world. Now, embodied but not simulated, well, if you think about these sort of old-fashioned industrial robots, like an industrial spray painting robot, so the car factories, the car comes along on a conveyor belt, and there's a robot there that sprays paint onto the car. But those robots, if you go to the Powerhouse Museum, you can see examples of these kind of robots. Often they don't have any sensors. They just carry out a predetermined sequence of actions. So if something went wrong and the conveyor belt came along and the car body wasn't actually there, they would just like spray into the air, sort of thing. And usually those robots are nailed to the ground for safety reasons. So robots like that, we consider, obviously they're embodied, but we generally consider them as not situated because they don't react to changes in their environment. They don't observe changes. They just like go through a predetermined sequence of actions. So again, you can always make objections or boundary cases and so on, but these are the two. Basically, there is a real distinction here. And yeah, this issue about the high-frequency stock trading system, apparently in the 80s, there's a story about one of the first people who was doing this high-frequency automated trading in the 80s. Before that, humans would type in a stock trade at a keyboard, and this guy kind of pulled out the keyboard, and he just had software deciding which trades to make, and it would interface directly with the network. But then people from the regulatory authority came and complained, and they showed him a clause in the contract that said that all trades had to be typed at the keyboard. So what he did was he actually built a special robot, a special kind of robot that had one finger for each key, and the robot would type the things into the keyboard. And he said like they had to put the robot in a special soundproof room because it sounded like a machine gun. But somehow they were complying with the regulations. Yeah. Yes.
I mean, there's the software that drives the robot.
Right.
And like what part of it is considered to be embodied or unembodied, and like this robot typing on the keyboard. I mean, where do you call the embodiment? Is it sort of in the robot itself, like the robot talks, the actual software running in the embedded device? Or is it actually running externally, just communicating via Wi-Fi?
It's a good question. I mean, I think we tend to think of the embodiment as actually the robot itself, the hardware.
But the thing
But
making the decisions and dealing with the environment, the sensors and so on, is that then running in the same thing that's running around? You know what I mean?
well, it's a good question. I mean, you mean whether the I mean, if the dog was switched off and just sitting on the floor, would it still be embodied? I suppose it would be embodied.
Let's say you couldn't fit all the software or,
Right.
supercomputer that's running this thing. Let's say it's connected up to something in the cloud.
Oh, yes. Oh, well, it's a good point you mention, actually, because with the dogs, it was not like the processing by the rules, had to be on the robot itself, I guess. But with the F180 League, it was allowed to have the processing on an external PC, and then it would send instructions to the robot. So what's embodied? Does it matter where it's running?
In terms of the decision-making process, where's that going on? Is it, are we saying it's embodied because the decision-making process is within the device that's then running around? I mean, what are we calling embodied?
I guess this is really the main. If you're writing the software, if the software is going to be causing an actual robot to physically move around, I guess we would call it an embodied task, even if the software is actually running on a PC. Yeah.
The sensors are in the environment and being affected directly by the environment, so it's kind of like the sensors in the environment.
That's right. Yeah, I think the task is, we still consider the task of controlling the robot is embodied, regardless of where the software is really running.
So when we're talking about embodied, we're relating back to the task of ourselves.
That's right.
So it's about the task, it's not about necessarily how you implement the task or dealing with the task, but what the actual task is and how it's affected by the environment.
Exactly. Good. Okay, so at this point, I think we'll take a 10-minute break, and then we'll come back and talk about different agent types.
Hi, how you doing?
Good.
Me again. I wanted to ask you last week, but you're very busy after lecture actually. You mentioned Stephen Pinker.
Ah,
You had
yes,
disagreements with him, and it occurred to me, because I know he's been a long time critic of deep learning and neural networks and so on. I mean, another one who I know is a very good terms with him is Gary Marcus. Do you know who he is?
Yes.
Yep. He's maybe a bit infamous
I'm
within
familiar
the deep learning.
with his. Yeah. Oh, okay.
He's
Yeah.
infamous within deep learning, I think, because of how critical he is. I'm actually just curious, what are your disagreements with Pinker?
Sorry.
What are your disagreements with Pinker? I'm just curious.
Well, I think that, okay. Oh, well, okay. Well, there's this whole thing about whether language is innate.
Yeah.
So I guess Chomsky had this view, and I think it's fair to say Pinker supported Chomsky's view that language. God, there's so many different issues. I mean, okay, first of all, Pinker, well, the evolution of language. So they have this sort of naive idea that, there was some mutation and someone was born who could, like blue eyes,
Yes.
I mean, blue eyes, someone was born one day who had blue eyes, it's like a single gene mutation or something.
Yes.
They sort of think about language in the same way, which doesn't really make sense. I mean, I think language evolved over a longer period of time than with some evolutionary pressure somehow. But then as far as this mind thing, it's this question about what they call universal artificial intelligence. So this is the more interesting question perhaps, is are there certain universal principles that could be applied to learn anything, or Pinker's view is that Like, there's like a vision processing system and there's a language processing system and there's something else and you kind of patch them together.
Yes.
I tend to have the other view I tend to more think that there's universal principles. And I think that it's still a minority view, but I think it's a more respectable view than it was a few years ago, this universal idea.
Yeah.
But it is related to this language thing, because that's the other thing, is that Chomsky and Pinker... Chomsky always had this idea, they talk about universal grammar, right? And then, there's certain principles that are... Okay, there are certain principles that are common to all human languages, I accept that.
Yes.
But Chomsky always said, well, you could invent, Martian languages which are different, but he never sort of gave an example of a Martian language.
Yeah.
And so I guess that it could be that these so-called universal features are really just what naturally emerges from the need to communicate something based on a sequential sequence of symbols and so on. Maybe that's all there is to human language. Maybe there isn't anything more specific than that. And when you look at made-up languages like Klingon is the way they looked at the extreme. Klingon does conform to universal linguistics, but at an extreme.
Yeah.
Like they took the most unlikely, like the word order. Most languages are subject, verb, object, or subject, object, verb.
Yes.
Klingon, they decided on verb, object, subject. There's only, 6 known languages that use that word order, but there are some.
Yes.
So it was always they chose things that are rare but do exist.
Yes. I mean, something that occurs to me, Pinker appeals to evolutionary biology to sort of all his arguments.
Right.
But it occurs to me that, one, it's kind of a truism within biology, new functions are basically reused old functions.
Right.
Teeth are modified scales, wings are modified arms. It
Yeah.
occurs to me, obviously, brains probably evolved first for vision and for movement. But any new feature was probably, you took some part of the brain, which is vision, and then you reworked it for language. Which leads me to think, as far as neural computations go, there must be some common thread going for all these different things. You know what I'm saying? Because people talk about the canonical circuits.
Yeah.
And there must be some reused computation for us to break those different functions. I guess I'm kind of trying to appeal to something like a universal computation system instead of computations for a whole bunch of
I think that's right. I think a lot of these things are based on vision. And, we can talk more about this later, but if you look at, it's interesting, if you look at the part of the brain that controls language, your chimps make noises, but they're very simple, right? If you look at the part of the brain that controls language in the human, and you ask, well, in chimpanzees, what does that part of the brain control in a chimpanzee? It actually controls the movement of the hands. So there's a widely held view that probably sign language came first and then developed into...
I think it has been observed that sign language shares syntax with spoken language, which seems to suggest that the brain isn't just about speech, it's about the range play is about just speech, it's about something a bit more universal.
Yeah, we could talk later about it. Yeah, it's very interesting.
One quick question. So, how intelligent does an embodied program have to be? Like, can a cron job that wakes you up at 7 in the morning or something like that, regularly scheduled, pre-programmed set of instructions now, sort of intelligent programs? What's the threshold?
That's a good question. Yeah, I mean, we don't think this again. Once we know how something works, we don't think of it as.
Yeah, right. Because
A lot of things.
When I was a real little kid, we had this heater that would turn on and off depending on the temperature.
Yeah,
And I thought that was really cool. And then my father explained to me, well, they have two strips of metal and one of them expands faster than the other. And once I realized that, I thought it didn't seem that cool anymore. So once we know how something works, we're not sort of impressed by it. But I guess it's still situated.
It's not interacting
It's
with
still
the
embodied, but
embodied
it's
because
not very intelligent, I suppose. But
Yeah.
it's still embodied.
It's still
somehow.
embodied.
Yeah.
Okay. Yeah. I just wanted to clarify if there's like a minimum sort of like requirement or like
Right.
a threshold or something that makes like a program intelligent.
Yeah.
Do you have like any sort of opinions on that? Like
I'm
what-
not sure. I mean, just because it's embodied, in general terms, if something's embodied, it's probably more difficult than if it's simulated. But not something. It might be very simple, even that's not always true. Yeah, something might be embodied but still be very simple, and that's true for all of those attributes. I guess.
Hi, I can't find this course in Open Learning.
Ah, really?
Yeah.
But you're enrolled in the course,
Yes.
or when you created an open
Yeah.
you went through Moodle to.
Yeah.
Okay, look, send me an email and
Yeah.
then I'll try to get the open learning people to sort it out for you.
Thank you.
Good. Where are we? Okay. So, that was how to classify tasks, and now we look at different agent types. And in this course, we're going to talk about 5 different agent types. So reactive agents, model-based, planning agents, game-playing agents, and learning agents. So this is slightly different from what's in the textbook. It's pretty close. So the textbook uses the term reflexive agent rather than, I think, simple reflexive agent rather than reactive agent. So we prefer the term reactive agent. And then the textbook also distinguishes between value-based agent, and they talk about model-based agent and then a value-based agent. They make a little slight distinction there, but we kind of merge them into one and just treat them both as model-based agents. So these are the 5 agents that we're concerned with. So this again is the same picture I showed of the generic agent. So the simplest agent just connects perception directly to action. So it takes in a perception of the current moment, and chooses an action. So it's this very kind of closed loop based on a policy or a set of rules which are simple to apply. Right? Now, I'm just going to show you a couple of like I say, the textbook calls these simple reflex agents, but we consider that to be a bit derogatory because sometimes these things can do surprisingly sophisticated things. So I just wanted to show you a couple of examples of like reactive agents in in action. So this is some work we did years ago about simulated hockey. I'll talk more about this later on in the course, but basically you've got this agent that just observes the world through very simple sensors, and it's trained by like an evolutionary algorithm, and eventually at the beginning it's sort of fumbling around, but eventually it manages to learn to knock the ball off the wall and score a goal. Let's just have a look at this again. So this is the beginning where it hasn't learned very well. This is somewhat later where it manages to score the goal, but slowly, and here it sort of smoothly hits it towards the goal. And this is where it nudges it off the wall, and this is where it accidentally hits it towards its own goal and then goes and kind of saves it. And it's trained just like as a single agent, but then once you've trained two of them independently, you can put them together in a rink and have them play against each other, and you get a quite impressive looking game emerging. So at this stage I won't go into all the details of how this was trained, but the point is that this is really a reactive agent, and yet it manages to do a pretty good job of the task that's assigned to it. Now this, I don't know if I have found another video of this, but this is sort of these little Lego robots. At the beginning, the pucks are separated. At the beginning, the pucks are separated all around the field, and then gradually these robots kind of pile up the pucks into piles. This is another example of something that can be done by reactive agents. So they can do pretty reasonable things, but there are certain things that reactive agents, it's more interesting to look at what the limitations are of a reactive agent, what it can't do. So this this is the sort of mistake that a reactive agent might make. Let's say you have a robot that's trying to go towards the goal. A reflex agent might just go directly towards the goal, and then it gets kind of stuck here, and then it sort of doesn't know what to do. And this is this image is taken from a paper about robotics, but interestingly, you get the same phenomenon sometimes with animals. If you take a domesticated chicken and put it in this situation where it can see over the top of this barrier but can't walk through it, and you put food here, the chicken will kind of it'll first walk directly towards the food, it'll realize it's stuck, and then it'll just sort of wander around in a random pattern until eventually, by chance, it happens to get to a place where it has a direct line to the food, and then it'll go there and get the food. But if you put a dog in the same situation, the dog will start running towards the food. At some point it'll realize there's a barrier in the way, and then it'll just sort of swerve around the barrier. So this kind of gives you an example, tells you a little bit the limitations of a reactive agent. And in the Wumpus world, maybe we can see this a bit more clearly if we when we got to here, if we just knew that we were somewhere and we were detecting a smell, we wouldn't be able to tell that the Wumpus is in that square. In order to deduce that, we have to remember the fact that we previously went up here. So we have to remember where we went before, and we have to well, first of all, we have to kind of keep a memory, a bit of a map of our environment. We have to remember where we went before and what we observed when we were there. So you have to remember that we first went up here and detected a breeze, and then we came back, and then we came over here and detected a stench. It's only when we remember all of those things that happened in the past that we can figure out that the pit is here and the Wumpus is there, right? So a reactive agent would not be able to deal with that situation effectively. So in order to do that, you need to have some kind of memory. So for this, we introduce what's called a model-based agent. So notice we still got the perception and action. We still got this direct link between perception and action, because sometimes if there's an emergency situation or something, we need to have that direct link. You know, you put your hand on a hot stove, you have to be able to pull it away very quickly, or if a robot is about to fall down a staircase, it has to realize that quickly and back up. So you've still got this pathway here, but in addition, the agent is making a world model, which is often in the form of a map, but it sometimes is the form of a list of facts or other things. And so every time as it observes things, it's updating its world model, and then it can use the world model as well as the perception in order to choose actions. Okay. So by keeping a map of the places it visited and remembering what it perceived there, it can make these decisions. Now, but there are some limitations of a model-based agent. So this is this situation a little bit contrived, but just have a think about this. Let's suppose that you're in the Wumpus world and you've been to these squares but not those squares, and you detected a breeze here, here, and here, and a stench there. Can anyone think of a plan that's likely to succeed in this situation? Well, let's see what we can deduce about this. What can you tell me about this square? It's got a pit. What about this? What about this square? It's also got a pit. So we know that there's a pit here and a pit here. Now, is there a pit here? Yeah, there's no pit here because we didn't detect a breeze here. There's no pit here and there's no pit here. There could be a pit here. We're not sure. And then the Wumpus has to be here or here, right? So could someone tell me a plan that has a very high likelihood of success in this situation? Yes?
Go forward to the top one and then shoot your arrow across.
Very good. So we go back to the place where we detected the stench, and we say, okay, well, I know there's a Wumpus here or a Wumpus here. I don't know which one. But remember that I have an arrow and I can shoot the arrow. So if I aim in this direction and shoot, then if the Wumpus is here, then I'll hit the Wumpus, and then I'll be able to safely walk into the square where the Wumpus was, right? And then once I get to here, if I don't, it's possible the gold and the Wumpus are in the same place, in which case I can get the gold, or it's possible the Wumpus is here and the gold is here. Once I get to here, I'll be able to tell whether there's I could try to go through here and see whether the gold is there if I want. So that gives me at least a pretty good chance of getting to the gold. Now, of course, well, if the Wumpus was here but the gold was here, then shooting the arrow doesn't have any effect, but I'll still be able to get the gold. If the Wumpus and the gold are both here, then I won't get the gold. Okay, so it's not absolutely guaranteed to succeed, but it gives me a pretty good chance. But notice, in order to make these decisions, we had to really not just observe what happened in the past, but kind of plan what to do in the future. So we have to sort of reason about taking a certain path and then taking certain actions and then what we're likely to observe when we do those actions and so on. And so this is where we need like a planning agent. Yeah. Now, here are some other examples. If we want to play chess or we're trying to solve Rubik's Cube, we can't just sort of randomly move around. We have to really sort of plan ahead. And same is true if we want to cook a meal or assemble a piece of equipment or achieve a certain goal. For all these kind of tasks, we need a planning agent. Okay, so we still have the world model, but we introduce this extra module that does planning, and the planning interacts with the world model, and here we can better make a choice of action. Okay, so this is the planning agent. Now, we're going to see several examples of this throughout the course, but in general terms, the type of world model that you have influences the type of planning that you can do. So in the next couple of weeks, we'll be talking about graph search and so on. So the world model will be a set of states and transitions between those states. And then the planning that we use is state-based search. So it'll be depth-first search, breadth-first search, uniform cost search, and so on. If our world model is a dynamical system, a physical simulation, then the planning would perhaps consist of simulating the dynamics in that simulator and observing what will happen. This is relevant also to games like Infinite Mario and so on. Sometimes the world model is kind of a set of parameters, and then the planning is based on goals and utility, and then we'll look at logical agents, in which, with logical agents, the world model is actually like a list of facts that we know, and the planning will be logical inference to deduce things from those facts. And in fact, in the Wumpus world, we'll see examples of this as well. So with the Wumpus world, part of our world model is the fact that there's a stench here, and then we also have facts that say that if there's a stench in a certain square, there's a Wumpus in the neighboring square. And from that, we can deduce the fact that there's a Wumpus either here or here, and so on. So this fits into the same framework of having a world model and then having planning. Okay, I think we kind of covered this already. This is a sort of simpler version of the same situation. Here you would shoot the arrow and then move forward into that square. Okay, now there's this concept of faking it. Okay, so this is, let's suppose there are some situations where something looks like it's intelligent, but then you find out later that it's actually just following some simple rules. So if let's suppose that I ask you to write an agent to play this Wumpus World game, and it has to be a reactive agent. You just got to try to do the best you can. This is probably the best you can do. If I detect glitter, I just grab the gold. Otherwise, if I detect a stench, then I shoot. And otherwise, I just randomly move left, right, or forward, because that's probably all you can do. So then, if there is a possibility, if you detect a stench, if you happen to be facing in the direction of the wumpus and you shoot, there's some chance you may kill the wumpus, and that would give you a slightly higher chance of survival. So, I mean, it's possible you could implement this and see how often it successfully gets the gold. And if you watch this agent, there may be some situations where you watch this agent and it somehow manages to get the gold and come back, and it looks like it's making clever decisions, but actually underneath it's just following these simple rules. So what distinguishes this from a more sophisticated agent is that it's not flexible in adapting to new situations. So it may sometimes get lucky and happen to execute a good sequence of actions in a particular situation, but then when you put it in another situation, it may do something really, really dumb. Yeah. So, and you can observe this in nature as well. I'm always fond of telling this story about the wasp and the grasshopper. So there's this famous studies in the 19th century. People observed animal behavior and sometimes thought that animals were really intelligent, but sometimes they often turned out to be kind of faking it in this way. So there's this there's this famous case of this wasp that Charles Darwin observed in South America. This is a bit disgusting, but the wasp, when the wasp is pregnant and it's ready to lay its eggs, it goes out and it finds a grasshopper and it kind of stuns the grasshopper with some kind of poison and then wraps it up in a cocoon, and it drags it back to its nest, and then it lays its eggs inside the grasshopper, and when the eggs hatch out, they actually kind of eat the grasshopper from the inside out. So it's very kind of disgusting. But what's interesting about it is, like, when you observe this wasp trying to drag the grasshopper, it always drags the grasshopper backwards into the nest, and when it reaches the entrance to the nest, it'll put the grasshopper down, walk into the nest, like walk around the nest, because the problem is, like, some predator might hide in the nest waiting to attack the wasp, and because the wasp is dragging the grasshopper backwards, it can't look into the nest, so then the predator could come up and attack it from behind. So when the wasp gets 1 inch away from the nest, it'll put the grasshopper down, go into the nest, just check that there's no predator in there, and then it'll come out and drag the grasshopper the rest of the way. So when this was first observed, people thought, that's absolutely fantastic, that wasp is really, really smart. Right? But then in the 1950s, someone had the idea, well, I'll do an experiment while the wasp is in the nest. I'll just get a pair of tweezers and drag the grasshopper a little bit further away, so it's 2 inches away instead of 1 inch. And so what happens is the wasp goes into the nest, it checks the nest, it comes out, and when it comes out, the wasp is 1 inch further away. So what it does is it'll drag the wasp again till it's 1 inch away from the nest, and then it'll go in to check the nest again. And according to this paper, the experimenter was able to repeat this on one occasion 47 times, and every time the wasp exhibited exactly the same behavior. So I've always sort of imagined, I like to sort of, I always anthropomorphize this as like obsessive compulsive behavior. I love to imagine this wasp, it gets to the entrance of the nest and thinking, maybe this time I'll just drag it straight into the nest. Like, it's only 1 inch further away. I've already checked 47 times. Surely there's no predator in. But somehow it just, I better go back and check one more time. So this is one example from nature where something looks intelligent but is really faking it. And someone emailed me last year, some people have disputed some of the details of this WASP experiment, but it's an interesting example. Okay, where were we? So we got reactive agents, we got model-based agents, planning agents. Now, we tend to think of a game-playing agent as a different kind of agent because the task is so different. So what happens in this situation is that you're playing a game against an opponent, so your world model has to include a model of the opponent, because to play the game decently, you have to try to figure out what the opponent is likely to do, and then the planning in this case is special search techniques for adversarial games, minimax search, alpha beta pruning, Monte Carlo tree search, and so on. Now, finally, we get to the learning agent. Now, from our point of view, we normally think of learning not as a separate module, but as a way of improving the existing modules. And we have different types of learning for these different modules. So we can improve perception with statistical learning, we can improve the world model with Bayesian learning, we can improve planning with inference learning and action with reinforcement learning. For this course, we're going to concentrate on these two things, statistical learning and reinforcement learning. So it's mainly about perception and action, but these things are also exist. Now, learning, it seems a bit funny to say this, but in the 70s and 80s, learning was very, very frowned on. Most AI people didn't want to look at learning. The idea was, expert systems were the rage. The idea was you just should consult an expert and try to implement their knowledge in the computer. Now, of course, we have a completely different view. So learning is often necessary in agents because it's difficult or impossible for humans to design all aspects of the system by hand, and the agent may need to adapt to a changing environment without being reprogrammed by the human. So if you move, a typical example is if you have a vacuum cleaning robot and you move to a new apartment, you want the robot to be able to wander around by itself to figure out the layout of the new environment. You don't want to have to pay an engineer to come and reprogram the robot for the new environment. Now, just one final thing about learning. When we talk about the complexity of a task, we have to distinguish the complexity of learning from the complexity of application. Right? So that simulated hockey player that I showed you, at the time it took a few days to train that. I mean, the computers were much slower back then. It could probably be done in an hour or two now. But even so, there's a significant amount of computation involved to train the agent and learn those parameters. But once it's learnt the parameters, then the strategy can be deployed very quickly in real time. So you've got to be mindful of that distinction. And again, this is why I love the textbook. I love Russell and Norvig, but they tend to put more emphasis on search, and they don't, even though they would call this a simple reflex agent, nevertheless, there's been quite a bit of effort. There could be quite a bit of effort that's gone into developing that reflex agent. And we will have I'll talk a little bit more about, I'll have a separate section on reflex agents, but we'll probably get to that next week or so, not this week. Okay, so any questions about this? So finally, sorry, just to wind this up, in the tutorials, one of the questions is about how to classify a task and what kind of agent you would need to do that task. Now, I guess for any serious task, it stands to reason that a planning agent would do it better than a reactive agent. So you could say, well, you always need a planning agent, but the real point of that exercise is to try to articulate what it is about a certain task. You know, if you look at a particular kind of task, what is it that a model-based agent would give you that would give you an advantage over a reactive agent? You know, so how would a planning agent help you to solve that task better? How would learning potentially improve your agent? Yeah, so it's more about exploring those kind of issues. Any questions about this? Good. Okay, well now we'll go to prologue. Now, okay, so the first assignment has been released. I'll put up a notice about it, but if you go to Open Learning, I think you can find it. If you click on assignments, you should be able to find it or a link to it. You have until the end of week 5 to do this, and this is just 5 exercises in prologue programming. So you have to write 5 little predicates here. Each one is just a few rules, 2 or 3 or 4 or 5 rules. And have a look at this, and there's all this explanation here. Now, I'm not going to go through all the details of this prologue programming because, okay, again, if you go to the Open Learning website, if you go to Learning Activities, you can see pages about prologue. So there's these 3 from last week's module, and then there are 3 more, and each one has a little video. So please go and watch those videos because they contain all the details. What I'm going to do here is just kind of give you a high-level summary and draw your attention to the most salient points. So last week we let me just log in here. Okay, so if you remember what happened last week, so we looked at these, we talked about different queries, who's teaching what class, and we talked about how Prolog processes a query by doing a kind of tree search. We looked at arithmetic, how you have to use is to force something to be evaluated. We looked at these different operators, less than, greater than, equal, not equal. Notice how less than or equal to is written in prologue. It has to be, it's equal less than, because if you wrote it the other way around as less than or equal, it would look like an arrow, and the arrow actually has some other meaning. So you've got to be a little bit careful about that. Well, now, so that was last week. So for this next module, we're looking at recursive structures and recursive programming. So we look at trees, and then we look at lists. So lists are a ubiquitous thing in Prolog. Lots and lots of things are based on lists, but we also find it interesting to look at trees. So a tree structure here is defined as follows. So we want to be able to store a binary tree in Prolog. So this is an example of how that tree would be stored. So a tree is in the form of the word tree, and then an open bracket, and then you have a left subtree and a middle element and a right subtree. So this tree is represented as, this is the left subtree, the middle element is Fred, and that's the right subtree, and the left subtree is itself a tree whose middle element is Jack, and then the left and right subtree are empty. So we use empty as just this kind of placeholder to say that there's nothing there. So really, sometimes when we draw the tree, we leave out the empties and we just draw it like this. There's Fred, and then the left child is Jack and the right child is Jill, but underneath these empties are in there. So if I just look at okay, now a couple of things along the way. So I type prolog, and then if I do -s trees.pl, it'll load that. It'll load these facts and rules into memory. So now if I say so it said my tree, and then this is the tree that was. So here's another example of a tree. It's got a plus, and then there's the left child is a 7, and the right child is this tree with a minus and a 5 and a 3. So you can start to use this kind of tree to do arithmetic. And if I say my tree X, it'll come back and tell me that X is equal to this, because I put in this fact here that my tree of this particular tree is true. And then I can do various things with trees. So one thing I might want to do is check the size of it, count the number of nodes in a tree. So here this tree has 5 nodes because we don't count the empties. And so this is a little rule that says this. So, okay, so two things. So first of all, we often have a base case and then a recursive case. So the base case here says that the size of the empty tree is 0 because it has no nodes. And then if a tree is not empty, it must have a left subtree and a right subtree. So what I have to do is I count the number of nodes in the left subtree, and I call that left size. And I count the number in the right subtree, and I call that right size. And then, okay, so this is the left subtree. So the left subtree in this case has 1 node. The right subtree has 3 nodes. So to get the number of nodes in the whole tree, I add those two together and then add one more for the root. So once I know what left size and right size are, I compute left size plus right size plus 1. I make that equal to total size, and then that's the size of the whole tree. So a couple of things to notice here. So you get this recursive structure where you have a base case and then you have a recursive case. The recursive case calls the same predicate itself on the left and right subtree. And the other thing to notice is the way information tends to flow in Prolog. So it often follows this kind of pattern where it goes down, around, and then up. So L and R come down to here, and then it computes left side and right side, then left side and right side come to here to give us total size, and then total size comes back here. So you get this kind of scooping action where the flowing of the information. Okay, so again, like if I want to run this, I can say, okay, my tree X, and then tree size of X S, and it comes back and tells me that that tree is of size 5, and if you want to see what's going on under the hood, you can trace it. So it's a bit hard to show these side by side, but that's the tree there. So what's going on here? It says, okay, I first have to calculate the size of this left tree, which, and then this is also like empty 7 empty, so the size of the empty is 0, and so the size of the left tree is 1. So at this point it's figured out that this left subtree has size 1. And then it computes the right subtree, and here it's figured out that this node has size 1. And there it's figured out that this node has size 1, and then it'll add those together, and it figures out that this subtree has size 3, and then it adds the 1 and the 3 and the 1 and tells you that the whole tree has size 5. Okay, so look at the video and trace through this and see how you go with it. Okay. Well, now we move on to lists. Okay, so a couple of things about these lists. Now, there's let me just get out of here. Okay, so if I run Prolog, right, so a list in Prolog is, right, in the exercises, if you work through the exercises, you'll define lists with a different syntax. So that's just useful because it kind of gives you a way of implementing some of these standard functions in a different way. But the standard way that lists are, so I think they're written like this. But the standard way that lists are stored in Prolog is like this. You have square brackets, and then you have the items in the list one by one. Now, there's a couple of different ways to construct lists in Prolog. Now, one is the dot notation. Now, the dot notation, if you want to use the dot notation, unfortunately, like the modern versions of Prolog don't support this because the dot is actually being used for a different purpose. So if I type this into Prolog, it comes back with this error about dict. Now, if I do prolog minus minus traditional, that means it kind of emulates a bit of an earlier version of prolog, and then I can use this notation. So this dot, every list has a head and a tail, and the dot notation takes a head and a tail and puts them together to make a new list. So if I take an empty list and add 3 to the front, and then I add 2 to the front of that, and then I add 1 to the front of that, I get this list 1, 2, and 3. Okay, so if you want to use the dot notation, you have to use this minus minus traditional. Now, for those of you who are running on your laptop, to have this minus traditional flag, you need to run it from the command line, not by double-clicking on an icon. And so then you have to know the full path of where prolog is stored, and there's some little pointers. If you look in the prolog exercises, there's some little hints there about where prolog is likely to be stored. So that's, I mean, you don't have to use this dot notation in the, but if you do happen to use it, you need to run it in this traditional mode. And if you want to use this dot notation in your assignment, the assignment will be tested with the minus minus traditional flag. So that's okay. All right. Okay. So just to get that out of the way now, the other probably better way to construct a list out of a head and tail is using this notation here. So if I say, oops, I've killed it. If I say x equals 1 pipe 2, 3, this is writing the list as a head and a tail. Okay? And you can use this notation, you can probe it in any way. So if you say I have a list 1, 2, 3, 4, and I want to split that list into a head and a tail, I can query it like this, and it comes back and says, okay, the head of the list is 1, and the tail is 2, 3, 4. You know, if I say, and you can ask it any way around you want. So if the tail is 2, 3, 4, and I add a certain head, the head is going to be 1. Right? And you can also, and this will be useful for the assignment, I can put a couple of, not just the head, but I can put 2 or 3 items at the front and then a tail. So if I say x equals 1, 2, and then 3, 4, 5, it understands that this is obtained by taking the list 3, 4, 5 and then putting both of these elements on at the front. Right? Okay, so one thing we can do with a list is to find out the length of that list. Right, so here's a program that calculates the length of a list. Now, again, this is a recursive program. You have a base case and then you have a recursive case. So if the list... Sorry, let me just run this. Here's another tip. If the name of my file is lists.pl, if my file has a .pl extension, I can load it by typing lists with rectangular brackets, and it'll load that file, and this is useful if we want to load multiple files within a program. Yeah, I can also say consult lists, and this is useful because if I've edited, let's say I consult and then I go and edit the file list.pl, I remove some rules and add other rules. When I do consult, it will actually it'll forget the rules that I've deleted and load the rules that I've added. So this is a way of updating without having to exit Prolog and fire it up again. Yeah. Okay, so let's say I want to calculate the length of this list here. Well, here's another thing. This is not a function. I actually have to say I want the length of this comma x, and it'll come back and tell me what x is. Now, how is this achieved? Well, the base case tells me that the length of an empty list is 0, and if a list is not empty, it must have a head and a tail. So I calculate the length of the tail, and then I add 1. All right, so if let's call this A, B, C, D. If I trace this, that is interesting. Length, okay. Sorry, I didn't think about this. There's a built-in procedure called length. Let's change this. My length. Yeah, okay. I can't trace length because it's built in. But my length should have the same behavior, and I can trace it. So there's a longer discussion about this on the video, but one helpful way to think about this is like you're unrolling a carpet. So, and we always unroll it from this left-hand end. So we don't think of this as a whole list. We just say, well, we think of this as if it's just all rolled up, and so the first person unrolls it a little bit, and he sees the A, and then he passes the rest on to the next guy, and the next guy unrolls it, and then the last guy's just got an empty list, so he figures out that has size 0, and then the next guy says, well, that part was 0, and I'm adding 1 item, so this is 1. The next guy says that was 1, and I'm adding another 1, so that's 2, and then 3, and then 4. So you can kind of see this recursive procedure in action. Then the next example is like concatenating two lists. So an example of this would be if I want to concatenate 1, 2, 3 with 4, 5, 6. You see, I made the same mistake again. I need to have the answer. I need to give it a variable so it can store the answer. And it comes back. When I concatenate those two lists, I get this list. And again, you can probe this in any way you want. So if you say, well, what would I concatenate this with in order to give this list, it can come back and tell you. Or if I give you the back end of the list, it'll tell you the front of the list, but I'm not sure if it'll work this way. You know, what two lists can I concatenate to give that list? Oh, okay, then it gives multiple answers. I can concatenate the empty list with this, or this with this, and it goes through all the possibilities. Okay. Now the code for this again, there's a base case and a recursive case. Now, the important thing to remember here is it's easy to add and remove items at the front of the list, not at the back of the list. So we always try to operate on the front and not the back. So it doesn't really matter how long the second list is. The important thing is the size of the first list. So if the first list is empty and we concatenate it with the second list, we just return the second list. That's the base case. And then the recursive case, well, if this list isn't empty, it must have a head and a tail. So we take off the first item, we concatenate the tail with the second list, and then when we get back the answer, we add the first item back at the front. Okay. So again, you can trace through this. Again, look at the video, trace through this, and you can see how this is working. And there's another example where you add up the items in a list. Well, there's this slightly more complicated example where you're given the cost of each item. What I've given here is, this is a simpler version where you're just adding up the items in a list. So again, the base case here, if there are no items in the list, then the sum is 0. Otherwise, you split it into a head and a tail, you figure out the sum of the tail, and then you add the head, and that gives you the new sum. So if I want to sum this list 1, 2, 3, 4, the answer is 10, and if I trace it, you can see how this is working. It starts by stripping numbers off from the front and then waiting to get back the answer until the list becomes empty. So when the list is empty, the sum is 0, and then you think about this as like 5 guys who are waiting in line. Each one is waiting for the answer from the next guy. So this guy gets the 0 and adds the 4. This guy gets the 4 and adds the 3. This guy gets 7 and adds 2. And this guy gets 9 and adds 1. Okay, now this is a bit more sophisticated, removing duplicates from a list. So let's say that there are multiple let's see. Okay, so let's say the same item might occur multiple times in a list. So there's A, B, C, but then A occurs again. And what I want to do is, like, if an item occurs multiple times in the list, I want to get rid of it and just be left with one copy of each, a new list which has one copy of each item. And it comes back and says, okay, B, C, A, and D, right? So how does this work? Well, here we need two recursive cases. If the list is empty, if the original list is empty, the new list is also empty. Otherwise, I split into a head and a tail. Now here I'm using the predefined function member that tells me if something's a member of the list. So this is saying, okay, if this first item occurs again in the rest of the list, then I know this first item is appearing somewhere else, so I can throw away this copy of it because it occurs somewhere else. So all I have to do is remove dupes from the rest of the list and return the answer. This is saying, okay, if the first item is not a member of the rest, then I'm going to need this first item because it doesn't occur anywhere else. But what I'm going to have to do is remove the duplicates from the rest of the list, and then when I get the answer back, I'll stick this first item back onto the front, right? So again, you get this kind of flow where you go down here to compute new rest, and then after you get new rest, you put the first item back. Okay, so finally, issues about the cut operator and about efficiency. Well, first about singleton variables. So you'll notice what happened, I think, with one of these. Right, so okay, so first of all, let me just go back to the assignment spec. So yeah, so this example of concat, this concat is actually emulating the functionality of a built-in procedure called append. So there's a built-in procedure that will append to lists, one list onto the back of the other list. Now, for the purpose of this assignment, we're not allowing you to use append because we want you to physically manipulate the list using the head and the tail, or the first two items and the tail, because it's more elegant. So append is useful in situations where you don't know, you're sticking two lists together and you don't know how many items are in the first list. But if you know that there's like one or two items in the first list, it's better not to use append. It's better to do it directly. So you're not allowed to use append in your assignment, and there's these other find all and map lists you're not allowed to use either. So just make sure that those don't occur in your file. And we're also not allowing you to use a semicolon. So I talked about this last week, that it's better style to split something up as multiple rules rather than putting or in there. So make sure you don't have any semicolons in your code, and we're not allowing you to use the cut operator either. So I'm going to tell you in a minute what the cut operator is, but you've got to avoid it in the assignment. Okay. Now, sorry, where was I? Yes, style. That's the other thing, is we insist that your assignment must compile with no warnings. Now, I actually got a warning when I loaded one of these things. I got a warning. I think it was lists.pl. No. Yes. notice when I loaded list.pl, it gave me this warning, singleton variable head. So if I look at this, you notice this variable head occurs here and it doesn't occur anywhere else, right? Because I'm just computing the length of the list. It doesn't really matter what the value of the first item is because I'm just counting up the number of items. But usually in Prolog, we don't, if a variable only occurs once, usually a variable will occur at least twice in a rule. And if a variable only occurs once, it looks suspicious, and the compiler picks it up because normally it means you've made a mistake. Normally it means you intended to use the variable twice, but you forgot to include the second occurrence. Or you intended to include it twice, but you made a spelling mistake. And you spelled it wrongly, and that's why it only occurs once. So for that reason, it's considered bad style to include something once, and that's why it gives the warning. Now, the way to get rid of that warning is to put an underscore in front of the name. So if I put underscore head, I think that should suppress this warning. Yeah, you see it didn't give me a warning there. So keep that in mind, especially with your assignment. If there are some situations where you really do want a variable to occur only once, and you want to tell the compiler, yes, I know this occurs once and I'm okay with it, and the way you do that is you put this underscore in front of the name, okay? And that's in these notes here. And then, okay, so finally we get to the cuts and the efficiency. Now, the cut operator, sorry, this graphic somehow disappeared from here, but it's still visible on Open Learning. So let me just, I will fix the other one, but let me just find it for you on Open Learning. It's down here. Okay, so lectures. Okay, so what does this cut operator do? Well, normally Prolog looks for an answer and then it looks for multiple answers. It looks for one answer and then it looks for another answer and then another answer, and it keeps going. But there are some situations where you don't want that to happen. There are situations where you say, I only want one answer and I don't want you to go and look for any other answer. And you can force that to happen by using this cut operator, which is an exclamation mark. So this is an example. So if you remember when we did lectures called X, it came back with two different answers. If I say lectures called X and then I have a cut, it only comes back with one answer, right? It says, I only want one answer to this, and you're not allowed to go back and look for another answer. Now, this is a little bit what happens here, maybe it's better if I show you a good, so there's good uses of cut and there's bad uses of cut. So the cut operator is kind of a thorn in the side of Prolog. Without the cut operator, Prolog is this beautiful, elegant, kind of formal language and so on. And putting this cut in kind of makes it a little bit of a hack in a way, but there are some situations where the cut is very useful. So maybe I might twist this around and actually show you a case where it's useful, and then show you examples where it's not recommended. Okay, so let's have another close look at this remove dupes. Remove dupes. So we look at these two rules. So remove dupes. What will happen here? Oh, well, sorry. First of all, let me just say what the cut says. So the cut says, once you reach the cut, so if I ask Prolog remove dupes something, 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 if I ask it to try to satisfy this rule, it can try different values of these variables while it's trying to satisfy this rule. But once it reaches the cut, two things happen. First of all, whatever values it has for these variables, when it reaches the cut, it's not allowed to go back and try any other values. Those values are frozen, and it can't go back and change them. That's the first thing that happens. The second thing that happens is that if this rule fails, it's not allowed to go back and try to satisfy remove dupes in some other way. Right? So it sort of cuts off exploration in two different ways, and this is what this graphic is meant to look like. If I say lectures cod course and then cut and then say studies student course, here it's found that cod lectures 9311. So it's found a value of course that satisfies this, 9311. Now, once it gets to the cut, it's not allowed to change that value of course and look for a different value. It's stuck with this value. Now, here, it's allowed to try multiple values of student. If there were two different students studying 9311, it could find both of them. But in this case, there is only one. But then when it comes back, effectively this part of the tree is pruned off. It's not allowed to look for that part of the tree because of the cut. It's not allowed to look for another value of course. And it's not allowed to go back and try to satisfy this in a different way. Yeah, so that's what's happening. It's cutting this off. Okay, so where are we? Why would this be useful in remove dupes? Well, you think about, if it's a short list, it doesn't really matter, but let's say the list has 100 items. So you feed that 100-item list, it takes off the first element, it's got 99 items left. It searches through those 99 items to find out whether the first item is a member or not. Now, let's suppose it isn't a member. So then this rule will fail. And then it comes down to this rule, and this rule starts with not member. So what it does with this not member is it tries to satisfy member, and if it fails, then it decides that not member is true, right? So this not means that you can't prove that this is a member. So, I mean, 100, maybe 100 isn't enough. Let's say there's a million items. It goes through and searches a million items and finds that that item isn't a member, and then it goes back and repeats exactly the same work again to look for whether that item's a member, and it turns out it's not a member. So it's kind of doing a lot of wasteful work here, and this slows down the program. Now, so an alternative that does the same thing is here. I put in a cut in this rule, and then I take out the not member from here. So what happens here is if that first item it tests whether the first item is a member of the rest of the list. If it's a member, then it'll just remove dupes from the rest of the list, and everything's fine. But if it's, and then it won't be allowed, because of the cuts, it's not allowed to come back and apply this rule, right? So this rule won't happen. If the thing's not a member, this will fail, and then it can move down to this rule. So Prolog always applies these rules in the order in which they're written. So because this has failed, the only way it can get to this rule is if that thing has failed. So it can only reach this rule if the first item is not a member, so I don't have to check it again. Okay, so this is an example of a good use of cuts, because it speeds up the program and takes away unnecessary computation. Now, having said that, here are a couple of sort of bad cases of cut. You know, like max. Here's a program that calculates the maximum of two numbers. If A is bigger than B, it returns A. If A is less than or equal to B, it returns B. I could get rid of this and replace this with put a cut here and write it like this, but it's sort of, this is not advised because it makes the code more complicated to read, and if it does speed it up, it just speeds it up by a tiny, tiny microsecond that's not really worthwhile. But the reason I'm mentioning this is sometimes when people start to write Prolog, they have this urge to put cuts all over the place. You know, when we talked about this later, it actually, when you think about this logically, if one of these rules succeeds, necessarily by logic the other two must fail. But sometimes people think, oh, I want to make sure that only one of these will succeed, so I'll put a cut at the end of each rule. And so you should resist this urge to put too many cuts in your code. And in order to do that, we're forcing, in fact, that for this assignment you have to do it without using any cuts. Okay? Even though I'm telling you that there are some cases, theoretically, where cuts may be justified, but you have to not use the cuts. Okay? One final thing is about the order of the rules. So I can write this remove dupes in a couple of different ways. So this is interesting. So my original code, I had member first rest, and then I had remove dupes. So what I've done here is I've swapped the order of these two rules. I'm doing the recursive call first and then checking member. Now logically these two things are the same. Swapping these two rules doesn't make any difference, but in practical terms it can slow the program down. So let's say I do remove dupes. Well, if I have a very short list, it's not going to make any difference, right? But I can type in a longer and longer list. Let's see. That's pretty quick. Now you can see, you can feel that it's going a little bit slowly. It took about a second to come back with that answer. And this is taking about 2 seconds. So it's giving the right answer, but it's taking a noticeably long time. And the more items I add, the slower it's going to get. So why is it doing this slowly? Well, you think about what's going on here. It first does all the computation necessary to remove the dupes. In the original version, I first test whether the item's a member of the list, and only then do I remove the dupes. But here I do all the computation necessary to remove the duplicates from the tail, which may take a really long time, and afterwards I test whether it's a member of the list. It may not be a member. This computation has all been wasted because I've got to come down to this rule. And so you can, if you actually sort of figure this out, it gets to every time you add, and if you do have a list where everything actually is unique, every time I add a new item, it'll actually double the computation time. Yeah. So this is something to keep in mind. Again, like, watch the video for the details of this, but this is something to keep in mind for the assignment. There's a couple of list places in the assignment where swapping this order may speed the thing up a lot if you have a really long list. But this is a separate issue from the cut. This is just about the order of the rules, of predicates in the rule. Okay. So, like I say, this was meant to be just an overview. You should have a look at the videos for the details and work through the exercises. Does anyone have any questions about this? Yeah. Okay, I just want to do one more thing before we go, something very quick, because next week we're going to be talking about search algorithms. So this is just an example of the kind of, again, this is, I wish we could, I hope we can hear the video, I hope we can, oh God, what happened? Oh. Oh dear. Okay, something weird happened here. Got a bit of a technological glitch here. Let me see if I can switch to the internal computer. Okay, so next week we're going to be looking at state space search. And how to kind of navigate our way through a search space. And this is we're going to mainly be looking at this example based on the map of Romania. But this game is interesting because the first ever paper published on this topic in 1967 was based on this sort of children's puzzle called Missionaries and Cannibals. And this is extremely offensive, and I think we probably can't hear that. But the idea here is that you've got 3 missionaries and 3 cannibals, and they have to cross to the other side of the river. And what happens is, if you leave, only 2 people can be in the boat at once. And if you leave the missionaries outnumbered by the cannibals, then the missionaries are going to get eaten by the cannibals. Right? And the idea is to get everyone over to the other side of the river, right? So let's think about this. Now notice, if they're in the boat, it doesn't matter if they're in the boat, they're still considered to be on the other side. So if I send this cannibal back, these guys are still going to be eaten, okay? So can someone give me advice on how to proceed here? We send the missionary back. Okay, what should happen now? No? If I send 2 missionaries, the other guy's going to get eaten, right? What happens if I send a missionary and a cannibal? So what's the solution? Okay. We could send the 2 missionaries. This is the part I've always been confused about. You'd think the cannibals could just wander away. The missionaries would be stuck there, but anyway. What should happen now? Very good. Okay. Very good. So you can, this is one of the cheat questions coming up, is kind of to draw this state space.
like running in my computer
Is that the code copy from the one?
from it's the single branch.
Oh yeah. I mean, I think maybe it's an issue that it's not instantiated. Atom inspector. Oh. Oh, is this the right file? Fact that
There's no fact there. That's that you can not relevant.
yeah, you need to load the lists.
So I need to have